Hey everyone, this should be the first video you're watching for this week. We're going to start off with just a little quick review of what we need in a circuit, and then we'll talk about the individual components of a circuit with their diagram representation. So first thing you have to remember about circuits is just what you need to make one. Um, Really, I guess the most important part of a circuit is the voltage source. Voltage, also known as potential difference, comes from batteries. Um, I've got a D battery here. I'm going to use it to make a sample circuit in just a minute. But as far as our circuits go, they come from batteries, which are several cells lined up, perhaps. Those cells or batteries provide voltage, which is also referred to as potential difference, to a circuit. That potential difference is not energy, but it is related to energy. It's a measurement of joules per coulomb, so energy for each charge that flows through. So you can kind of get away thinking of voltage like energy, even though it's not exactly energy. So another component you need in a circuit is the current. You need the electrons that carry charge to flow through the circuit. So the electrons carry charge intrinsically, but they will also carry a certain electric potential, that's the voltage, as they go around. Now they're going to lose that voltage as they pass through resistors. And then they'll gain voltage back as they pass through the battery. Which brings us to resistance. Every circuit needs resistance that comes from resistors or light bulbs. Light bulbs or any component you plug into a circuit will also carry its own resistance. And this resistance kind of inhibits the flow of current. Without resistance, electrons flow at not light speed, but not too far from light speed. When you have charge moving that quickly through a battery and around circuits, that's going to cause electrical fires very quickly. That's called a short circuit when you have a circuit that doesn't have resistance in it. And then, of course, you need the wires themselves to be able to, for these electrons to flow from the battery to the resistors or components you want to power. So I've got all the components we need right here. I showed you the battery. This is our voltage source. I've got a wire. And I've also I don't have a resistor, but I do have a bulb. This is a bulb I unscrewed from a flashlight. So to just see a quick, simple circuit, I'll take my voltage source, the battery. I'll connect it straight to the bulb itself. I don't need a wire connecting it. I can just put it straight on there. Now, this isn't powering the bulb because, of course, I need for a circuit for the electrons to have a chance to go from one of the battery to the other through a resistor. So this is just kind of one half of the connection. I need to also make a connection from the resistor back to the other end of the battery. I'm going to use the wire to do that. So I've got the flashlight bulb on one terminal, wire connecting that to the other. My light's on. Here, let me give you a little bit of a better look here. Here, it's a flashlight. So the way any light bulb works is kind of covering with my hand, but we need to connect. It's kind of the side of the bulb into the bottom. The side of the bulb for one connection and the bottom to the other. If you look closely at a light bulb, when the wires go through the filaments, one wire goes to the bottom, one wire goes to the side. If you have wires going straight through the bottom, it's not going to actually go through the filaments of the light bulb to make it glow. You're just going to pass right through it. It's like it's not even there. You'll see a little bit more about that when you eventually get to your simulation assignment later. Okay, another point to review is Ohm's law, really just an equation relating voltage, current, and resistance. Ohm's law is read three different ways. The way I like is the voltage of any single circuit component equals its current multiplied by its resistance. So the ratio between voltage and current is resistance. Again, you got three versions of that equation. As is true with any three variable equation, you can rearrange algebraically to set it for any variable you want, but V equals IR is the way I like to think of Ohm's law. Um, we've also got some circuit symbols here. You have these symbols on your reference tables. The way we schematically represent components of a circuit isn't by drawing them as they look in real life. You don't actually draw a battery in a circuit. You just draw, for example, here, the kind of a combination of two cells, series of short and long lines. Again, you'll get used to these schematic representations. We've got our cell, battery, switch, voltmeter, and ammeter. We haven't used those yet, but we will eventually. Resistors are just jagged lines. They are identical to lamps or light bulbs as far as functionality goes. The lamp's advantage is that it glows, so you have an indication of the power of that component. And then there are variable resistors. We will not use those, but an example of a variable resistor in real life would be like a dimmer switch. You turn a knob on a light bulb or a lever up and down, and the light gets brighter or dimmer. That is you changing the resistance of that light bulb in order for it to gain or lose power. So just if we're trying to imagine how to draw a circuit diagram, you can try this yourself right now if you have just a scrap piece of paper in front of you. Let's say we want to draw a circuit with a single battery. Of course, you always need a battery in a circuit, with one wire connecting the battery to the resistor. So you can try that out now. Draw a battery with a symbol connecting it to a resistor with one wire. So I'll show you the symbols again if you want to try this right now. We then want to take this resistor, use a wire to connect to the other end of that first resistor to another resistor. And then we're going to take this second resistor with yet another wire and connect it to the other terminal of the battery. So hopefully, you're either imagining this or you've actually drawn it out. It's always nice to make a couple of labels in your diagrams so that we can keep track of everything. We like to label the battery V just to indicate that that's the source of voltage, and we'll label each of the resistors accordingly, just R number 1 or R number 2. If you've done this correctly, your circuit diagram should look something like this. In real life, circuits are never this, right angled. The wires are kind of, curving all over the place. But in schematic representations of circuits, there are always nice right angles